Okay, good afternoon, everyone. Thanks for joining for the sixth week, or the seventh week rather, of the 8-week digital series. So far, we've had an overwhelming response out in reference to our digital series. So we thank you for continuing to join week after week, and certainly we thank all those that are resharing the broadcasts that are published on Mondays. This week we have a very special guest, and this is our CTO, Geoff Peddle. And Geoff has had a really great career in machine learning. He has worked at Google, he's worked at IBM, he worked at SAP or Ariba before it was acquired by SAP. So he's got deep industry knowledge and has a special place in his heart for machine learning. Today's presentation is all about what's possible via machine learning and the emerging concepts. So please submit your questions throughout the presentation. I'll gather those and I'll ask those to Geoff at the end of the presentation. Without further ado, here's Geoff Peddle.
Thank you, Matt, for that kind introduction, and thank you everyone for joining us today. My primary goal with this webinar is to try to help you develop a bit of an intuitive understanding of artificial intelligence. I'm going to do that in large part through analogies, that is, drawing comparisons between AI and things that we are more familiar with. The reason for this is that AI is very abstract. It can't be readily observed with our five senses. For example, with the picture of a computer on the right, if I asked you whether that computer is currently running, say, Microsoft Office or the latest machine learning algorithm, it's difficult, if not impossible, to say. I think many of us, myself included, have a difficult time with abstraction. So I'm hoping that by comparing AI to things that we're already familiar with, that I can help build some useful intuitions about it. First, though, I wanted to talk about an important caveat. One of the things that we'll see is that powerful AI models can't be readily understood by people, even by the people who build them. We internally are using some models with more than 100 million parameters. You could think of that as a computer having a rule book with 100 million somewhat arbitrary rules telling the computer what to do. That's too many rules for a human to keep track of, so we let the machine learn these rules by giving examples of the types of situations we want it to handle. That's what machine learning is in some sense. It's the computer learning what to do from examples. And our jobs as the builders of these systems is to specify the architectures for the rules, things like the sequence in which they could be applied, what the rules can do, and so on. And so what analogies that I'll be talking about will hopefully help us gain some intuition. It's also important to understand that there's limits to our knowledge. This turns out to be one of the things that people are much better at than computers. It's not always easy for us, but we're better at knowing what we don't know. So I'm not trying to tell you that we know what we're doing and we understand the systems we build. I feel I have an ethical responsibility even here to tell you that we know what we're doing. And part of that is that we're aware that we don't fully understand the systems we've built. So yes, we know what we're doing. And no, we don't fully understand the systems we've built. I think it's important that we admit that and that it's better than not talking about it. This is an important part of the conversation around AI, but it's not just an AI issue. I think it probably applies to most large-scale entities. For example, this week, we welcomed 8 new students to our R&D team with backgrounds as varied as computer science, software engineering, linguistics, and neuroscience. Right now, we're working at home because of the pandemic, and so for the first time, we had to ship their laptops to their homes, and one of the laptops was late arriving. It was delayed for about 4 days for unexplained reasons. Something went wrong in the delivery system that was responsible for shipping that package to us, and it probably wasn't an AI issue. Once we acknowledge the limitations, we can start thinking about what actions we can take to mitigate them. And there's 3 things that are important: measuring the uncertainty, watching out for edge cases, and being prepared for unintended consequences as we change the system. To deal with uncertainties, we use benchmarking. We periodically test our system and then score it to see how often it's correct and how often it's wrong. One part of our system, for example, is responsible for figuring out the name of a company given its website URL. What we'll do is we'll randomly select 100 websites, and then we'll score how well the system does at getting the right answer. Our current system will typically get the right answer around 93% of the time for a task like that. Sometimes when it's wrong, it's close. For example, missing a name from a multi-part name or giving an alternative secondary name. Other times it's completely wrong. For example, returning the name of the company that built the web page instead of the company itself. Fortunately, that doesn't happen very often. To deal with edge cases, we primarily use monitoring. We're constantly monitoring our system and looking for outliers. These could be individual values or aggregate statistics that are unexpected or unprecedented. It could be a task that's running longer for usual or shorter than usual. Um, when we investigate these outliers, when we identify these outliers, we investigate them to understand what happened and whether or not it impacted any of our data, for example. And when we find problems, we fix them as top priority. We're constantly changing our system to improve it, but with a complicated system, there's often unintended consequences. Sometimes a change in one area will have negative repercussions in another. To make sure that we handle situations like this, we're constantly checking with each change that we make to ensure that we understand the overall impact on the system. One of the things our sales team says that I really like is that our data isn't perfect, but we're on a journey to improve it. And through this process of prototyping changes, measuring the impacts, and then only releasing them to production in cases where the impacts are positive, we can make sure that we're always going in the right direction. So in summary, part of knowing what we're doing is knowing what we don't know and having processes in place to mitigate that risk. All right, so our agenda. In the first section on patterns and party games, I'm going to try and give you a sense of the variety of ways of instructing computers and some of the trade-offs involved. It's about the continuum from traditional computer programming through to the most advanced machine learning models. In recent history of AI in 2.5 slides, I'm going to go over some of the big successes of the last decade and talk a little bit about what's behind some of them. In the birds and the bees, I'm going to try to put together AI. I'm going to try and put AI into a little bit of a larger context and talk about what we should hope for from our computers. There's a couple of different directions that people come to AI from. Most people probably associate it with computer science, but there's also a lot of overlap with statistics, and some people come at it from neuroscience and other places. You can think of statistics as trying to make sense of the world from data. You can think about it in terms of recognizing patterns and then trying to take advantage of them to make informed choices. There's an old adage, red sky at night, sailor's delight, which means that if there's a red sunset, the weather is likely to be good the next day. Now, the mechanism for this has to do with dust particles. When the weather pattern to the west, which is where weather systems tend to come from, is a high pressure system, there tends to be a lot of dust particles in the air, and those dust particles lead to a red sunset. So that's the red sky at night. And the sailor's delight is saying that when that happens, chances are the next day will be nice as that high pressure system moves in. Now, the people who first started saying that probably didn't understand the full mechanisms behind it. They just noticed the pattern, red sky at night, nice day the next day. And a lot of what we do with computers can be thought about that same sort of thing. When we get a computer to recognize a pattern like that and make a good choice, we can call that AI. Here we have a range of board games or party games. On the left, we have snakes and ladders. So the way snakes and ladders work is you roll the dice and then you count off the number of squares. And then if there's a ladder, you get to go up. And if there's a snake, you fall back down. It's a game of chance. There's no strategy involved. In the middle, we have a game of checkers. Each piece has a limited number of moves that it can make, typically one or two, in some situations zero, in some situations 3 or 4. It's a fairly simple game with limited choices. And then on the right, we have chess, a more complicated game with a larger variety of pieces and pieces that can move in a larger variety of ways. and it quickly becomes limitless almost in terms of the possible outcomes and the complexities. Now, when we think about coming up with computer programs to approach these different games, on the left, a traditional software approach makes sense. Here, we can tell the computer exactly what to do, and it can play the game correctly. As we move over towards the right, that becomes more difficult to do. And so, to get a chess program to work, you might come up with a few rules. For example, if you can jump another piece, then always do it. If one of your pieces is about to be jumped, then move it, and maybe looking a move or two ahead. If you can move a piece into a safe space where it'll be able to jump next time, then do that. And we could come up as a human with a set of rules and an order in which to apply those rules. And that would probably play a reasonable game of checkers. The next kind of level of complexity would be to let the computer maybe decide what order to apply those rules in, or maybe let the computer come up with a few simple rules in that pattern on its own. And then let the computer learn how to apply the rules. And so the way something like that would work is you let the computer play against itself, and you let a computer program with one set of rules play against a computer program with a different set of rules, and see who wins. And whichever rules win, then those are looking like better rules than the other rules, and you try different combinations until you come up with a good set of rules. As we get into games like chess, it becomes really difficult to try to come up with a set of rules that plays even a reasonable game of chess. And so here we have to really release more of the control to the computer and give it more flexibility in terms of the things it tries and the ways it looks for patterns. And as we do that, we lose control and even understanding about what the computer is doing. Now, a question might arise, where does AI begin in this? Does it really matter? Typically, we wouldn't say that traditional software where we're telling the computer exactly what to do is AI. If we have a few rules that we come up with, maybe it's AI, maybe it's not. As we start getting more control for the computer and it making more of its choices from data, we move into an area where people would largely say, yes, that's AI. But it's not necessarily a point where, at one moment it's not AI and at the next moment it is. And does it really matter? That's something we're going to talk about. So here's some pictures of my children, and I think about this a little bit as an analogy for what's going on here. For traditional programming, like we were talking about on the left, it's kind of like having a baby. And with a baby, you have to do everything for it to a large extent. And you can do everything for it. If you want the baby to go upstairs, you pick it up and you take it upstairs. It's pretty simple. As your children get older, it becomes you lose a little bit of control and you try to communicate with them maybe through setting or negotiating rules. Go to bed by a certain time, or do half an hour of homework, or don't watch too many videos. The way we might program a chess program, has some commonality with that. And then as the children get older and move on towards being adults, it's no longer maybe a great strategy to try to give them rules to evaluate every situation. We begin to have to release control and allow them to make decisions based on their own experiences. And that's a little bit of what we're doing with the computers as well. In this, there's a trade-off really between how much control or transparency that we have and how complicated the situations that they can handle or model are, how varied the patterns. And so you can see up in sort of the top left corner on the axes, up high on transparency and low on complexity, we have traditional software. And then as we start, instead of programming it in a traditional way, we start setting up rules and letting it make decisions by evaluating rules, we begin to give up control. As we go further down and add more rules and start beginning to require the computer to learn the rules because we can't keep track of them all anymore. The transparency goes down, but the ability to handle complicated systems goes up. And if we take that, kind of further out to the extreme, where a lot of the recent work has been done around deep learning and things like that, with millions of rules or hundreds of millions of rules, um, they can recognize very complicated and subtle patterns, but how they do it and what they'll do with a particular picture becomes much more difficult to predict. At Tealbook, we use all of these tools and a lot of data in the work that we do around building our supplier profiles. And it's not really a question of one being better than the other. It's a question of choosing the appropriate approach for the problem at hand. And so we have an application team that builds, a large number of capabilities, including areas around analytics for giving insights into the data and discovery for searching for and finding maybe new suppliers. A lot of that capability is built on top of the data that our machine learning team comes up with. And so for something like an address extraction or finding social media links, we used a fairly simple set of machine learned rules, to do some of those sorts of tasks. We have a domain matching capability where we get supplier data supplier master data from our clients that's often very noisy or missing fields. They may know the name of the company. Hopefully they know an address or something like that, maybe a phone number. Sometimes there's spelling mistakes in the names of the company. Sometimes the address is old. Um, and we try to map that onto the data that we know about suppliers so that we can do things like find duplicates and fix mistakes. So we use rule-based systems for a lot of that work, but with some machine learned rules around that. And then out at the far end, we use some of the most recent and most powerful deep learning models with, tens and hundreds of millions of parameters to build up a semantic representation of our suppliers. And then we leverage that for things like finding important keywords to describe the supplier or similar suppliers, which is a feature where you may tell us, one supplier that or two or three suppliers that are in a particular area, and ask the question, what other suppliers in the system are similar to those suppliers? And in order to do that, you need to look beyond just the words that they use. You need to have a semantic understanding in many dimensions around what that supplier's capabilities are in order to be able to find similarities. And sometimes we combine these things together. So our B2B classifier, it's what we use to populate our database. We look at hundreds of millions of web domains, and we don't want all of them. We don't want the news sites, we don't want the blog sites, we don't want the adult content. And so we have a classifier that looks at a domain and decides, is this the sort of B2B supplier that would be of interest to our clients? And we find that somewhere in the 2% or so of websites satisfy that. And in order to do that, it's a combination. We use both a semantic representation of the supplier from a deep model, plus some hard-coded rules that we fully understand to make sure that in the final choice, we have a good understanding about what the system is doing. So it's not a question of one is better than the other, and it's not even necessarily a question that you only use one to solve a particular problem. All right, so that's a little bit in terms of the broad scope of different approaches to AI. I think it's safe to say that in the last decade, AI has been dominated by an area called deep learning. This success was marked last year when Professor Geoffrey Hinton from the University of Toronto and two of his former students were awarded the Turing Prize, which is computer science's highest honor, and it was for the work that they did around deep learning. Two of the AI problems that have really been moved forward as a result of this work have been around images and text. Now, at Tealbook, we use the deep learning models to build our semantic understanding of the text and the suppliers that we deal with. Here, though, I'm going to focus more on the recent successes around images because they're more visual and they're easier to kind of show and understand. The image successes that also have come a few years earlier than the language successes. I would say there's about 10 years of history of applying these things around images and closer to 4 or 5 years maybe to applying it to text. But they've followed remarkably similar paths. And one of the first really kind of breakthrough models that we've used is called BERT, that was developed originally at Google, and it achieves the same sort of record-breaking performance on tasks such as text summary, question and answer, um, things like that. And our subtitle here is "Thank You, Gamers," and we'll see how gaming, in a lot of ways, really, helped usher in these advances in AI. So similar to how Tealbook uses benchmarks internally to understand our systems and how they're performing, the industry has also developed benchmarks uh, that allow us to track progress and compare one algorithm to another. And one of the main benchmarks around images is the ImageNet benchmark. And it consists of thousands of labeled images, really hundreds of thousands of labeled images in thousands of categories. And here you can see four categories. So the six images in the top left are around goldfish. To the right, we have artichokes. Below the goldfish, we have spacecraft, and then bottom right, we have bridges. And someone's gone and broken these up into what they think of as easier images and harder images. And you can see that they're from, lots of different perspectives. The number of kind of, background is sometimes simple, sometimes distracting, and quite a variety of for goldfish, quite a variety of goldfish. So probably the primary task in this benchmark is to take a picture, and sometimes you're asked to just like choose one category for it, and you either get it right or wrong based on the category. And sometimes you're asked to choose like one of five categories, and you get the right answer if you get any of those correctly. And you can see here, here's the leaderboard um, for the last 10 years or so in terms of performance on this benchmark. And you can see fairly steady performance from, improvements from about 50% accuracy up to about 90% accuracy. And there's a bit of a debate around how well how well people do on this task. But the general feeling is that, a typical person walking up to this task will get, somewhere around high 70s in terms of accuracy. Roughly the types of performances that computers were getting around 2015. And this, this type of trend and computers beating human performance, it's shared across a number of areas in terms of like handwriting recognition, speech recognition, and various language tasks. So you could ask yourself, okay, so that shows you the last 10 years. What about before that? The history before that is actually about the computers and the storage and the content getting to the point where the machine learning would work. And so here on the left, we have a graph. Um, on the bottom axis, we have years from about 2002 to around 2011. And on the left axis, the vertical axis, we have computing power on a log scale. And so each one of those increases represents kind of a very significant increase in power. And you can see in the blue line the rapid gains in the power of GPUs, which is what gamers use. And in the red lines, similar sorts of games, though not as fast in terms of the CPUs, which is the more flexible general processor on the computers. And these trends have slowed a bit in recent years, but they've continued to a large extent as well. Um, and then here we can see similar sorts of improvements in storage. Here we've got time on the lower axis and a log scale of cost per looks like megabyte for hard drives in the darker line, and then for the memory chips that you have in something like your phone in the green line. And you can see the same rapid improvement in decreasing cost of storage. And to go along with that storage, you also need content. And so there's a similar change that happened over this time frame where the World Wide Web provided a lot of content in terms of images and text and things like that. And that's largely what set up the successes that we've seen in the last 10 years. There have been improvements in the algorithms as well, um, but really what enabled the successes of the deep learning systems in recent years has been this improvement in the hardware. And so, for our next system, trying to sort of quickly talk through some of what's behind that. And we're going to start by talking about bees. So if we had a computer that had the same power as a honeybee, how many pictures would it need to look at to learn to recognize a flower? It's kind of one of those sort of interview questions that's gone out of favor a little bit. So a honeybee, it turns out honeybees have around 1 million neurons. Uh, For comparison, a human has maybe 88 billion neurons. So not, a particularly powerful computer. And if we look at the models that have been, achieving success on those benchmarks, they're a little bit more powerful than that. The best of them tend to have, 500 million or so parameters. Um, but there's some models, that do, roughly around what humans perform with around 3 million parameters. So our honeybee's a little bit underpowered, um, but something like a goldfish or a rat would have a brain that, if we focus the whole thing on the problem of image recognition, would have similar kind of capabilities maybe to our kind of world-class models. So how many pictures would the honeybee need to look at? Well, it turns out quite a few. If you look at how many images that the systems that I was telling you about have used to train, it's around 14 million just in the core data set. And a lot of times they train on images beyond that. And so you can see that the honeybee, it maybe gives you more appreciation for the natural honeybee because it's able to make much more efficient use, both in terms of, the hardware that it has in its brain, and especially in terms of the number of images that it needs to look at to learn things. And that's an active area of, both of those are active areas in terms of machine learning research, trying to come up with models that are more efficient in terms of data and also in terms of computation. Okay, and now in terms of the birds, when I was thinking about this presentation, a couple of birds happened to fly by me, and I realized that, maybe we could draw some analogies between birds and flight and, artificial flight. And here I'm using the word artificial in the same way you would use artificial for artificial intelligence. It's man-made flight. And in the top right, you have kind of a reproduction of a sketch from Leonardo. And you can see that Leonardo was originally thinking of human-powered flight, kind of, fairly closely modeling what he saw in the natural world. And that's not what happened. Airplanes have kind of, gone off in their own direction. And they haven't they've given up trying to replicate what birds do, and they've looked for using their own strengths, which are different. Are you a dog lover? Okay, so just a couple of a couple of slides to talk about how we see these image systems replicating and even perhaps exceeding human performance. But does that mean they are like us? And the first thing is, okay, well, are these systems really doing better than people? And it turns out that a big part of the reason they do better than people is because a number of the categories have to do with breeds of dogs. And if you don't recognize individual breeds of dogs, then you'll kind of not understand, you'll not be able to come up with the correct label for that category. So it's not necessarily that humans aren't as good at the visual processing as most of us don't know our dog breeds. And if you train a human to understand all of the categories, we're still capable of exceeding machine performance, on most of those tasks. The other one that I'd say is more interesting is this case. So there's a couple of things going on here. The first is on the left, we have a picture of a panda. And I think most people would look at that and be very confident that that is a panda. Um, Turns out this computer algorithm, which was a good one, was only about 57% confident it's a panda. So it was their first choice, but they maybe should have been more confident around that. But what happened next is really interesting. A researcher took some small changes to the image. They changed, one little piece here, a little piece there. And you can see the image on the right after those changes were made. And the way we look at images, we can't even detect the differences. But they chose the changes they made carefully to try to trick the computer. And here they succeeded. And I think most people would be surprised how much they succeeded. So they've convinced this computer with almost 100% confidence that the picture on the right, which still looks like a panda to me, is actually a small ape. And so I think that's an indication that while these systems are, able to do, a lot of the same tasks that we do, they do them differently. And it's maybe a mistake to understand them in terms of what we do. And I think that difference can actually be an advantage. The first quote here is from some work at MIT around developing new antibiotics. And what the professor is saying is that we kept coming up with the same molecules over and over again. And what we needed was novel chemistries with novel mechanisms that we hadn't thought of. And it turned out that because computers think differently, they were able to come up with a bunch of novel mechanisms that people hadn't considered. And the second quote is from a commentator watching Google's latest computer play chess. And they use words like creative, surprising, beautiful, and they credit it with coming up with a new way to play chess. And again, it's that difference as an advantage. And I love this quote. It says, "We know how to replicate human intelligence. They're called children." And her point is, maybe we have the wrong goal when we're trying to get computers to achieve general intelligence or be just like us. Maybe we should let computers become themselves, just like airplanes became themselves. And we gave up trying to build airplanes that flew like birds. And we leveraged the difference that was in the computers to allow them to become something new. And I think that creates a lot of opportunities, as we think in terms of transitioning jobs. One thing I like about this is intelligence isn't at the top of this management pyramid, it's in the middle. And as we think about how do we integrate computers and machine learning into our processes and workflow, one of the approaches I like to think about in terms of that is how do we make the human jobs more interesting? How do we unleash their empathy? How do we unleash their wisdom? And let the computers deal with hopefully a lot of the more routine tasks. All right, I'm going to skip the recap because I'm falling behind, and I'll go straight to questions. Thank you everyone for your time.
Thanks, Jeff. That was great. And based on the questions that have come in so far, you can tell that this is a very useful presentation for a lot out there. I think ML or AI in general is a term that's thrown out a lot without a lot of understanding of what's actually beneath the hood. So your explanation today, I can see, has already resonated with a number of the people on the webinar today. We do have 4 questions that have been submitted. If there are others, now is the time to do so. So I will get through the first 4. If there are some others that come through, then we'll ask those as well. And Jeff, feel free to answer as diligently or as high level as you would like on these. But the first is, we recently added ML talent to our data team. However, performance has been tough to grade because of the terrible state of our current data. How do you address this issue when data integrity gets in the way at Tealbook?
Yeah, so the data, a lot of this work has to start with the data. Like going for something like the chess example, it's hard to teach a computer to play chess. Um, it's even harder to teach a computer to play chess if it can't see all the pieces, or every once in a while it thinks the piece is here and it's actually over there. And these algorithms, by their nature, currently they're really inefficient in terms of data a lot of the time. And so, they tend to need more data. And if there's errors in that data, that just increases that further. And I think, a lot of times you have to go back to the source in terms of your processes, and see whether or not you can make changes at the source. And then, I work for Tealbook, right? Obviously, you can hire a company like Tealbook to come in a particular area to help you improve your data around that if you believe somebody else has better data that you can match up with yours.
Okay, along the same lines, we have a question, and this says, how much of ML utilization relies on data extraction capabilities?
Yeah, so on that continuum, the stuff towards the left was more kind of using the AI system to encode human wisdom or human understanding, right? And when I showed those image benchmarks from the last 10 years, that's really what transitioned there. The systems before about 2009, they used encodings of human understanding to try to recognize images or understand text. And in 2009, the computers got powerful enough and the data got plentiful enough that they could just throw the computer at the data and have them come up with much more powerful systems. Now, so it really, though, it depends on the complexity of the problem that you're trying to solve. If it's a simpler, more straightforward problem, like red sky at night, sailor's delight, then you can code that in, you can have the humans bring their expertise to that. If it's a much more complicated system, though, you're going to need the data and hopefully lots of it.
Great. We have another question here on a slightly different topic. So, could AI machine learning help identify behavior patterns due to economic trends? Also identify fair market value of procured items?
I mean, it really depends. I would say there's probably cases where that's true and probably cases where it's not. The chess programs, play tens of millions of games to learn rules as complex as chess. And so, we don't have that much economic history, maybe at a macro level, to really be able to, derive that from data, which is why for systems like that, you kind of have to encode, expert knowledge and look for ways to leverage expert knowledge. But in smaller situations like trying to predict movements of stocks and things like that, there are some people who believe that there's enough historical data that you can make small predictions like that and be right more often than not.
Okay, here we have another question that's specific to our industry. So often different suppliers are owned by the same overall parent company. How can AI help to identify supplier parent-child relationships so that procurement has visibility into the overall book of business being accumulated to the parent level, and can use this to leverage to negotiate based on aggregate spend of all combined children?
Right. So for something like that, I think you really need to look at the cost of having it wrong, right? Because different approaches are going to have different there's a trade-off between completeness and correctness. And different approaches are going to be different places on that. If you want to be more on the correctness side of that equation, I would say one approach would be to use AI to process filings from public companies at places like the SAC, where they list all of the organizations. So for like Honda Motors, I looked at it recently, and there were a couple of hundred subsidiaries, and some of them had names like Honda this or Honda that, and some of them were, just sort of unpredictable based on the name. And so, that's an approach that would cover public companies in terms of filing. And then all you have is the hard problem of mapping the companies in your supplier master to those names. And, something like Tealbook can help with that. On the other end of that, if you're not so much like it has to be perfect, but I'm looking for indications that, maybe will give me a broader sense, or that I can then follow up with people, you can do things like looking at web links. So, like there's IBM Canada, there's IBM UK, they own someone like OpenText or something like that. And a lot of times there's indications, in web links and other kind of web artifacts that you can leverage to predict that it's likely a subsidiary or a related entity. But it won't necessarily guarantee it, and it certainly won't give you the details like they own 53% or something like that. It's
Do
an
you have another?
interesting problem, though, and definitely an area that Tealbook does a little bit around that today, and it's an area that we continue to be interested in.
Thanks, Jeff. So now you have a question, talent related. So this says, can you please comment on the data science, engineering, AI, ML talent availability? You found 7 students to hire, which is fantastic, but there appears to be a talent shortage and a talent shortage for a long time. Any thoughts on this will shape up how you will attract and build into these capabilities, particularly if you are not near a talent hub such as Tealbook?
Yeah, I think there's a lot of things there. I would say culture is one of the real keys, especially I would say for machine learning, data science, things like that. I run my data science team very differently from my development team. Again, because of uncertainty. Development, you know, it's about execution. You have a set of requirements, and if you've been doing this long enough, you can estimate like how long is it going to take, and what's the direction from here to there. And a lot of times you're off, by maybe a factor of 2 or something like that. But it's fairly easy to say whether something's possible or not. I would say at this point, with a lot of the more interesting problems on the data science machine learning side, there's a lot more uncertainty around that. And so, you really have to have a culture that's about experimenting and taking risks, informed, smart risks, but you have to accept a significant number of failures. And I could talk about a lot of things that we've tried to do, that we failed, and some of them we failed multiple times and then succeeded, and some of them we've just failed at so far. And so, I think that culture will really attract people, trusting them when they get there. Good people want to work with other good people, so getting that first good person that'll be a bit of a magnet for other people to come follow them. Paying the salaries. Salaries are not cheap for this talent. And looking outside maybe the traditional places, or understanding exactly what skills you need. A lot of people think they need somebody with a PhD in machine learning, and those people are really hard to get. But rarely needed, especially when you're getting started. Having somebody who's got a bit of a programming background and some math skill, or, somebody with a master's degree or a couple of undergraduate courses, or somebody who, you already have who's, just really keen and willing to put in the time to learn some of this stuff, can get you started.
Thanks, Jeff. Last question for you today, and then we'll wrap up. So, and this question is back to the honeybee reference, but how long will it take for computers to catch up to the human brain as far as computing power is concerned?
Yeah, I think that one's kind of that one's tough. I don't know that it's close enough that you can really say too much about it. A lot of the trends that have been driving the exponential increase in computing have started to hit physical limits, in terms of like how closely you can put wires together, how quickly you can switch circuits on and off. And so, it's been a great run for, I don't know, 60 years or more. But you're starting to see some of those curves flatten off. And, there's things like quantum computing that, I think are so new that they're kind of unpredictable. So, I don't know that I'd want to make a prediction around that, but I think a lot of what some people have started recognizing in the last few years is that maybe that's the wrong question, and it's really, where should computers go so that we can work together to kind of accomplish great things together. And that doesn't necessarily mean computers having brains as big and powerful as people, or the sort of general intelligence that something like the Turing test might be trying to measure. It can be more kind of, celebrating the diversity of computers, and looking for ways that in harmony with us, that can make our lives better.
Fantastic. Thanks for your time this afternoon, Jeff. We really appreciated it.